got this charging capacitor that's connected to both trig and thresh, right, to 2 and 6. So let's imagine that the capacitor starts off discharged, okay? And let's imagine that we're charging it in the sort of discharged state. So it's charging from 0 volts. This trig, the trigger or 2 pin, is rising in voltage, okay? So at some point, that rising voltage is going to reach 1/3 of VCC, okay? So this lower third of VCC. At which point, this is going to go from, so before it reached that point, this was higher than, weird, this was higher than that. So plus was higher than minus. And when plus was higher than minus, S was set to true, right? And so the output was on. Once the 1/3 is reached, then this becomes false, right? So we get 0, and S is no longer set. So the set input to the flip-flop is no longer set. And this thresh is definitely going to be still set, right? Because we've got a much, pardon, it won't be set because this threshold is also the capacitor voltage, and it's below 2/3 of VCC. Okay, so this will also be 0. As we progress, though, as the capacitor charges more, then eventually we're going to reach this threshold. Okay, so 2/3 VCC, and this will be set to 1. Okay, and when the reset gets set to 1, the output gets turned to false, right? And it waits for a new S trigger. Now, once that happens, the output of flip-flop returns to 1. This inverted gate gets turned to 0, and it discharges, right? So it discharges, and we discharge the capacitor, which is connected to 2 and 6, remember, down to the point where S gets flipped on again, which is when it gets down to 1/3, the voltage gets down to 1/3 of VCC. Once that happens, this will become 1. S will then be true, and then this output will then become true. This will become so yeah, I think I said that wrong, but at this point we're going to switch back into the mode where we're charging up, okay, and then we're going to go through the same cycle repeatedly over and over again. This will get set. Once that drops, this will be 0. This will eventually get down to 1, and then it'll kick back and forth between these two voltages. So what we're going to get as the capacitor voltage then is going to be a charging up from 1/3 VCC to 2/3 VCC, and then a discharge to 1/3 VCC again, and then recharge back up, and it'll go back and forth. And these amounts of time depend on the resistors in our circuit. So we've got down here, yeah, well, we've got our two situations. So when we've got the discharge state, we've got a short between 7 and 1. Okay, so this connects to ground directly. And when 7 connects to 1, connects to ground, what that leaves is this capacitor and this resistor in parallel with ground. So the circuit that remains is effectively a capacitor, C1, in parallel with a resistor, this is ground, R1. Okay, and we've got no input, and it's just discharging. So it's discharging from an initial condition of 2/3 VCC down to 1/3 of VCC. So that's how. So it goes from we have 2/3 to 1/3, then back to 2/3, then back to 1/3. So during the discharge, this is the discharge circuit, we could predict this discharge circuit. We can predict what that discharge will look like. And then similarly, when it's charging, we've got effectively this short is not there, and there's no current flowing here. What we've got is a 9-volt battery that's going through R1 and charging up C1. So when it's charging, so this was the discharge, here's the charge. Charge circuit effectively just looks like a 9-volt battery connected to a resistor R2, connected to a resistor R1, connected to a capacitor C1, connected to ground. So these are our two circuits, and they actually are circuits that we can easily analyze. Now, so what we want to be able to do, and one of the things I'm going to ask you guys to do in this lab report, is to actually work out what the voltage across the capacitor should look like as it charges and discharges. So there's the discharge, there's the charge, and it switches back and forth when it gets between these two voltages. And that's where the timing is going to come in. So we're going to measure it. We're going to measure how it actually does with a given C1, and we're going to predict it, and we're going to plot them together. So it's pretty fun. Great. So when it's discharging, the transistor turned on and 7 connected to 1, and we've just got a discharge with time constant R1C. Notice that the two time constants are slightly different, because this is going to be R1C. This time constant is going to be R1 plus R2C. So they're going to be slightly different. The difference in resistance is pretty minimal, so it's not significant in this case, but it could be if those resistor values were different. Yeah, so it's much less than 1% in this case. Great. So building the circuit. We're actually going to build the circuit on a breadboard first. Okay, so build the circuit on a breadboard. We're going to switch in 3 different capacitor values. So C1 is going to be switched in, instead of 1 microfarad, it would be 1, and then 10, and then 100. So build your circuit on a breadboard. Try it out. Get it working. Once it's working on the breadboard, then we're gonna have you guys solder. So then we're gonna solder the circuit together, but only after you've done your tests. Okay, so better not to solder before you've done your gathered your data. So what we're gonna do is build one on the breadboard with a 1 microfarad capacitor. Measure the waveform using essentially the same VI. You can use pretty much the same LabVIEW VI that you created in the past. The last couple times you've used it to capture some data, and make sure that you get your nominal or you get your measured parameter values. So measure the capacitances and the resistances and what's your 9-volt battery really reading. It's best to get a reading when it's loaded, but yeah, so please try to get a measurement of the voltage when it's loaded. You can just get one measurement. You don't have to measure it constantly. And then the diode voltage as well. So go ahead and write those down. And then capture several periods of data for each circuit. So C1, you got your first capacitor in there at 1 microfarad. It's going to have one time constant, right? It's going to be relatively fast compared to the other two. And then your C2 is going to be a little longer. Your C3 is going to be a little bit longer. So capture data to capture at least a couple periods of that, and then save it and export it. So I want you guys to predict the entirety of the capacitor voltage waveform for each circuit. So I want you guys to actually do the circuit analysis for the two states, right? For the case of the charge and the case of the discharge. When you do that, you have to be able to determine when it's going to switch back and forth, right? So you know that once it gets if it's charging, once it gets to 2/3 VCC, it's going to start discharging. So you have to predict what that is, write an equation for it, and program that in so that you can plot it along with your data. And good. So plot your predictions and measured waveforms on the same graph. One graph for each circuit, 3 in total. One period is sufficient, but multiple is also fine. So you can do 3 periods if you want. A bit better would be to average multiple periods of measured data. So your prediction might match up with the measured data over a period, but over time it might sort of wander a bit. It's best if you actually take each period of the data and then average it with the other periods. But that's a little bit difficult because the sample rate that you're measuring at might not be exactly the same, might not be divisible by the period. So you might end up with some sliding that happens, and that's a little bit difficult to deal with. So even if you just do one period, it's not a big deal. Good. There was something. Oh, I wanted to make sure you guys are using. When you're measuring this, you might want to. So your timing of your VI. Remember that the VI has a timed loop, right? And we set the amount of time between each data point by setting the amount of time for each cycle of the loop. So 10 milliseconds was what we've used at certain points in the past. I would set that probably down to 1 millisecond. You may find, you can calculate what the time constant is going to be. You may find that for 1 microfarad, you might need to be a little bit even finer too. So explore that and see what you need in terms of resolution. It'll be pretty clear from the graph if you're undersampling, or at least it should be. You should be expecting to see something nice and exponential both directions. If it's not, then there's probably an issue, maybe with the sampling. Great. Okay, that's all I've got for this. Yeah. Okay. Go take some data. All right, have fun.